Okay, so today we're going to talk about accuracy, precision, and uncertainty. All right? Three very difficult to understand terms, but let me walk you through it. First off, accuracy and precision. Accuracy is how true a measurement is to reality. Okay, so if I were to make a measurement, all of these are about measurements. If I were to make a measurement, I want an accuracy is how close that measurement is to what the object actually is. For example, if I try to measure the length of, say, this eraser, I took my ruler and I put it up there, and I got that it is 13.73 centimeters. Okay, now what if this was actually 13.734589 centimeters? Way down. I wouldn't know that with this exact tool, so the fact is accuracy is just how close to the actual measurement of the length of this ruler I can actually get. Okay, now scientifically accepted values are scientists' current best approximations of nature, because it is true that there's going to be a point where, well, how do we know what we know? Well, it's because somebody at some point measured it, and the fact is that person may have made a mistake. So if it's scientifically accepted that this value is this value, that's because a lot of people have done it. So it's our best approximation of what nature actually is. All right? Now, precision is the reproducibility of a measurement, or rather how fine-tuned you can actually get it. So you really want something to be accurate, but you also want something to be precise. You want to be able to reproduce it, and you want to be able to reproduce it really fine-tuned. So let me give you a few examples here. Okay, let's say I make a series of close measurements. Okay, so I measure the mass of something, and it's 2.3. Then I do it again, 2.3. And I do it again, 2.3. And I do it again, 2.3. Now, I forgot to zero the balance, though. Zero. Make sure it said zero before I actually put it on there. So, are those measurements accurate? No. But are they precise? Yes, because I got the same result over and over again. They're just not accurate. So there's nothing wrong with my balance, I just forgot to zero it. So there's something wrong with the measurement, but the measurements are all still consistent. It's precise. Okay? We want precise, but we also want accurate. We don't want to be making that error there. Another example here. The accepted value of the density of water is considered 1.0 gram per centimeter cubed, or milliliter. Okay? The following experimental measurements were made: 1.0, 1.0, 1.0, 1.0, and 0.99 grams per centimeters cubed. Okay? Now, I got the same value for four of them, but then I got a slightly different value for that last one, but it's really close. It's only 0.01 grams per centimeter different from the others. Okay, now all of these are really close to the accepted value. Four of them are right on. So I would say that this is both accurate and precise, which is what we want. Okay, even though they don't match. That 0.99, okay, but we want them to match each other, but we also want them to be close to what the accepted values are, what reality is. All right, so 3 students conducted a laboratory experiment to determine the density of water. Okay. Once again, density of water, 1.000 grams per milliliter. All right? Student 1 got 1.0. Student 2 got 1.1. Student 3 got 1.5. Now, student 1 is accurate. Student 2 is close to accurate. Student 3 is way off. Okay, so student 3 is not accurate at all. Let me give you another example. 2 different students, not the first, same as the first 3, they conducted a laboratory experiment, again, determined density of water. Below are the results. Now, this time, student 4 got 0.975 grams per milliliter, really close to the accepted value, so accurate. Student 5 got 0.978 grams per milliliter, closer to the accepted value, so accurate. Now, both of these are pretty close to each other as well, so these two are precise. Okay? In fact, these are actually more precise than what we had before, because if you take a look at students 1, 2, and 3, they were able to measure it to 1 decimal place, okay, and they're all off by that 1 decimal place. If we look at students 4 and 5, they were able to measure it to 3 decimal places. And once again, that third decimal place is where they're off. All right? So if they are within each other on that last digit, on that last ability of what their measuring device can actually do, then they're probably pretty precise in terms of each other. The more decimal places you can get, the more precise you can get, and the closer and closer those measurements you can get, which is really nice here. Now, I've used this term already once in this video, error. Okay, error is the differences between observed values and what is true in nature. In other words, this is something is not accurate. That example of the balance that I did earlier, that was error. Okay, I forgot to zero it. That is an error. So it's causing that difference between observed values and what we have in nature. Now, there is actually a way to calculate how much error you have if you know the accepted value. It's called percent error. So percent error you calculate by taking the experimental value, subtracting the accepted value, finding the absolute value of that answer, and then dividing it by the accepted value and timesing it by 100. It's a percentage, so you want to times it by 100. So basically you take your value, you subtract the accepted given value, then divide that by the given value, times it by 100, and don't matter if it's positive or negative, just pretend it's positive because it's the absolute value. Okay? So let me show you how this one works. Same example, figuring out density of water. Remember, it's 1.000 grams per milliliter. Okay, student 1 got 1.25, way off. Student 2 got 0.97, pretty close. Okay, but we can actually measure or calculate how accurate they are with percent error. Sorry. So what we're going to do for this first one, 1.25, way off. Let's see how off he was. Well, 1.25 minus the accepted value, 1.0, absolute value of that. Make sure it's positive, so 0.25, divided by 1, 0.000, times 100 equals 25%. So student 1 was 25% off. Okay. Student 2, 0.97 is their value, minus the accepted value, 1.00. Absolute value of that, you're going to get a negative number for that. So absolute value there, divided by 1, times 100% equals 3%. So this is a way to show you how close each of them were. Student 1 was 25% off, student 2 was 3% off, and this is called percent error. Now let's talk about uncertainty when you're using your measuring devices. Okay, so I have the exact same amount in 2 different graduated cylinders. Okay, the graduated cylinder on the left has graduations from 400 to 500, and they go up by 10 every time. So it goes 400, 410, 420, 430, 440, 450, a bit longer line there for the 50, 460, 470, 480, 490, 500, like it keeps going up by 10s. Whereas the other one goes from 400 straight to 500. Now, if I were to try and figure out how much liquid is inside this graduated cylinder, first off, you measure the liquid, since it's going to kind of creep up the edges. You measure the liquid at the bottom of the curve. So we want to measure it way down here at this bottom of the curve. And you can see that it's between, this is 450 right here, so 460. So 460 to 470, okay? So it's between 460 and 470. It's not quite halfway. All right, so I'm going to estimate that last digit there in between the two as about a 4. So 464 milliliters is what I'm going to say that is. All right, now this other graduated cylinder over here, it's the exact same picture, but it doesn't have these graduations here. This is not as good of a device here. All right, since it goes straight from 400 to 500, I know you can see it way over here, but pretend you can't see it for a second. What would you say this is? Well, since we don't have those lines, it's a lot harder to estimate in between the 400 and 500 exactly. So I would go, okay, 400, 500, it's greater than half of that, so maybe 460. Okay, so with these 2 different devices, I actually get 2 different answers. And which one is better? It's this one over here, the one on the left. Why? Because I'm actually able to get a more precise answer here, closer to what it actually is. to what its accuracy is. So I was able to get a hundredths place, a tenths place, and a ones place here. Whereas with this one, I can get a hundredths place, but I am totally guessing on the tens place here. So I'm guessing on the ones place here because I know for certain it's between 460 and 470. So I'm guessing it's about a 4. In this case, I don't know anything between 4 and 500, so I'm guessing it's about 60 here, so I'm making an estimation here. There's no way I can get as fine-tuned all the way down to the ones place with something like this. All right, this is uncertainty. I'm very uncertain because of the lines here. Very uncertain about my measurement, whereas I'm more certain about the measurement here because of these lines here. So uncertainty, it's all about estimated or uncertain digits. You want to always measure one place past whatever the graduations are listed on your piece of equipment. Right? Every measurement needs to have one uncertain digit, one guess. It's always between the lines, where exactly between the lines it is. All right? That is your uncertain digit. So as an example, here's a ruler, not a graduated cylinder this time. I want to know how long this gray cylinder here is. And I'm going to say that this is in centimeters. So I've got 1 centimeter, 2 centimeters. Now this has lines in between the 0 and the 1 and the 1 and the 2. In each of these lines there are 10 of them, so those are millimeters. And this goes right in between these two lines. So that's 1.1, 2, 3, 4. It's between the third and the fourth. All right, so 1.3 something. Now this estimation here, this uncertain digit, is going to be my next decimal place. So I'm going to guess that is about an 8 or so. So I'm going to guess it's 1.38 centimeters. Now if somebody got 1.37 centimeters, that's perfectly fine. If somebody got 1.36 centimeters, that's also fine. Honestly, the exact distance between them, since we don't have lines, is really uncertain, and it's up to the person looking at it, right? It's all up to the person looking at it. So there is an element of opinion here when measuring something, and that's okay. You just have to understand it's always the last digit that has the opinion on it. So we know for certain it's 1.3 something. It's this last digit here that we're a little uncertain about. I'm saying it's about an 8, okay? Go ahead and pause the video for a second, and I've got 2 graduated cylinders. I would like you to try your hand at it. See if you can figure out what these 2 things are. How much water is in this one, and then how much water is in this one. And when you have an answer, go ahead and start it again. Okay, so remember that you need to read at the bottom of the curve. So at the bottom of this curve, it's about there. This is 30, this is 40, so that makes this 5, 6, so about 36 something. So I'm allowed to have 1 decimal here, 36 point something. And I think it's a little less than 5 here, so I'm going to go with 36.4, 36.3, 36.2. It just has to be 36 point something. And I would say 36.8 is probably but 36 point something here. You shouldn't have any more decimals than 1. You should only have 1 decimal here. But that last decimal can vary depending on who you are and kind of your own opinion. All right, and that's okay. That's our uncertain digit, is the 4, all right, in this case. Now with this one here, I'm going to go with 3.61 or maybe 3.6 right on the money. Now, if you think it is 3.6 right on the money, okay, but if it was, I mean, it could be 3.61, honestly, looking at it. It's all opinion here. Basically, because of the graduations here, the lines in between, you get to have 2 decimal places, okay? You get the 3.6 and then another digit. So if you think it is right on the line here, you want to include a 0 for that decimal place. You want to include it as 3.60 milliliters. Why that 0? That 0 indicates that you think it's right on the line, but you get those lines, so your estimated digit is the 0. Somebody else might have gotten 3.61 or 3.62. All right, but you think it's right on the line, so 3.60. Have that 0 there to indicate that you think it's right on that line. Okay? Thank you, guys.